Hello and welcome back to Statics. In this unit, we will be looking at equilibrium of a rigid body. This allows us to analyze various machines and mechanisms like this crane mechanism you see down here, or lift mechanism. This is a setup where we have a series of bricks being extended out over a distance, and very likely the question is how far can we reach with this, or at what angle can we reach with this and have it not tip over. This is something that this equilibrium conditions can be used to solve for. The two assemblies we're going to look at this unit are structures and machines. And they're somewhat similar in nature in that they're both made up of members that are assumed to be pinned together. And we'll get into that in more detail later. But they do differ in the nature of the individual components and in terms of their overall function. If we take a look at structures, structures are made up of what are referred to as structural members. They are almost always going to be straight. For example, if you see below in these two examples, this is a bridge truss and this is a roof truss, right? We can see they're straight members. And their function is either to support a load and or to span a distance. So in those situations, they rarely will be in motion, and in terms of their overall function, they're primarily going to be involved in civil engineering structures. On the flip side, if we take a look at machines, machines are made up of what we refer to as machine elements. And they're designed to actually affect the loads that are being applied to them. So they can transmit a load, perhaps moving a load from one location to another, or transform a load. So for example, we see below here a set of pliers and a series of pulley systems. In this case, we're amplifying the load or magnifying the load. In this case, we're transforming the load from a linear motion to a rotational motion. In general, machines are going to be in motion. That's how they actually transmit and transform loads. But keep in mind, the analysis that we're going to be doing is while they're at rest, so we'll still be using statics. Here are a few more examples. In all cases, they're going to be pinned elements, but we can see our simple truss here. Here's the type of loads that could potentially support. Here is a crank mechanism. This is a type of machine where this is rotating and converting over to linear motion. Here's a frame. This has multiple forces in it, similar to a truss, but these are actually 3-force members. Frames can actually be made up of bent members as well, meaning not straight members. So that kind of differs a truss from a frame. Here's another example of a pulley system, a little bit more complicated, designed to convert this force downward into raising this weight. So here's a variety of examples and a number more examples you can find in our textbook. So we're going to start with trusses. Trusses are probably the most common of our civil engineering structures. We'll be looking at 2D trusses in this unit. As I said earlier, the idea is that they are to support a load. Generally, you have an applied load. It could be a point load. It could be distributed load. And we're going to take that load and spread it over the entire structure. Right, and that allows it to support a heavier load than if it was just a concentrated or solid object. The other purpose, of course, is to span a distance. And the distance is greater in most cases than what a solid material could do. So a truss made of wood can span a greater distance than a wooden beam. A truss made of steel can span a greater distance than a beam made of steel. Right? As I said, they're going to be straight members. They have a uniform cross-section, and they tend to be relatively lightweight compared to the load they're holding up. So generally, we're going to assume they are weightless, although we do have techniques for incorporating their weight into analysis if necessary. They're almost entirely made up of triangles. And the reason for this is that triangles are a stable shape. There's no mode of failure that does not involve either the individual members failing in either tension or compression, or the joint failing. There's no way that a triangle can collapse. On the other hand, if you take a look at a square or a pentagon or anything with more than 3 sides, the actual structure can buckle and generally will fail at a much lower load. And you oftentimes see in square-shaped structures a support member going diagonally from the two edges to form a triangle. Because again, what we're looking for in almost all of our structures is that they are stable and strong. Trusses can be made of a variety of different techniques. Wood structures can be bolted or nailed together. Steel structures can be welded, riveted, or bolted. And there's a number of different ways things can be pinned together as well. But in our case, we're going to assume that it's pinned together with frictionless pins. And this is for analysis purposes. And we'll get a little bit into this assumption to make sure that it's justified in a little bit. I do recommend you take a look at our truss fabrication sidebar in the textbook. It does show some of the more modern manufacturing techniques and how wooden trusses are assembled and how they gain actual structural advantage. It's a good chunk of material, particularly for civil engineering students. As we've seen, trusses can be used in a variety of different ways. We see a bridge example here. This is a steel truss. We see building trusses here, mostly made out of wood on the right-hand side. We can also build towers and other type of support structures. Again, anytime you're looking to support a large weight over a large distance or a height, for example, in terms of a tower, a truss often is advantageous relative to trying to make it out of solid material. As we've mentioned, trusses generally have two purposes. They're either going to take your applied load and distribute it and essentially allow multiple members of the truss to support it. This allows us to have a far more efficient design, which makes trusses lightweight and able to hold up significantly more loads than solid material made out of the same weight. They also can span greater distances because they have this lightweight characteristics. The fact is solid members get heavier and heavier the bigger the distance they're trying to span, and eventually you get to a point where the beam itself is only able to support its own weight. So trusses are allowed us to do that in a way far more effectively than a long single member of the same material. We do generally make three assumptions when we analyze trusses. First, we assume that the bars or the structural members are connected at their ends and the joints are formed by frictionless pins. So that's what holds them together. Frictionless pins eliminates moments from our calculation. So that's an important assumption to simplify our calculations. We also assume that all the forces are acting at the joints, so that they're applied to the joints. This is required again for ease of analysis, but generally we have a number of joints in our truss, so there is a lot of different places we can apply them. Lastly, we assume that the entire truss, the members, the joints, and loads all are in a flat plane, a two-dimensional plane. So let's talk a little bit about these assumptions. So first off, they're necessary for us for our statics analysis. We do have limited tools at our disposal, so to make a truss analyzable using our static equations, we need to make these assumptions. But then the question is, are they justified? So that when we use this analysis, does the results we get, are they similar to what would happen if you analyzed a real truss, a real physical truss? And this is what we find. First off, the forces of the members, that when we use the pin assumption, how do they differ from the true value we would get in a real truss? And it turns out that they're relatively close. They don't differ substantially at all. So in that way, assuming that they're pin constructed does not seem to be a problem. Also, when you look at the weight of the member compared to the applied load, it's much, much less. Right? So in general, as long as we have a relatively lightweight truss, which is part of their definition, we can either neglect the forces, right, just assume they're equal to 0, or we can take the weight and divide it up equally and put the loads at the joints. So there is a way of incorporating truss weight into your calculation if you're so inclined. So with these first two assumptions, we can eliminate moments from our calculations, and as a result, the bars or structural members are considered two-force members or two-force bodies, which makes for a much easier calculation. So in fact, the members can either be in pure tension or pure compression. And as we said, the assumptions above are valid in almost all of our cases, so we can make this analysis simplification. Lastly, the third assumption is that we have a planar structure, that it's a 2D structure. And as you could see from the earlier photographs, and hopefully from your own experience with truss structures, they are relatively flat. That's how they're manufactured. And in fact, trusses are far more stable when they're flat. So most often, that's how they're designed. If we do get past or away from these types of structures, we can have ways of dealing with 3D analysis. We'll talk about that next unit, but it does get significantly more complicated. So here's some examples of some simple trusses. As you can see, they're named for individuals. In almost all cases, they're named for the engineer that invented them, usually back in the 1800s. We have Pratt and Howe trusses. They designed both roof and bridge trusses. We have what are referred to as a fan roof truss, a K bridge truss, and actually there are dozens of others that you can take a look at. There's a whole list of them on the course space that expands on these. These are designed in different ways based on the material they're constructed of and the types of load they're going to be supporting. Is the load going to be applied to the top? Is the load going to be applied to the bottom? Is it going to be concentrated in one location or another? It may have something to do with the function. So for example, in this fan roof truss down here, we want to leave an opening in the middle so people could walk back and forth in an attic space. So there's specifics to that design structure that are taken into consideration. Lastly, let's take a look at one of the simplest trusses. This is a Warren truss. Warren trusses are made up of equilateral triangles, meaning they have 60 degree, 60 degree, and 60 degree angles all around them, so equal angular, equilateral. That does tend to make the analysis relatively simple because if you think about it, if it's all 60 degrees off from each other, the analysis usually shows that the forces in each of these members are equal in many cases. Where you do have an applied load, that does become a little bit problematic. But in these simple areas here, when you do the analysis, oftentimes the loads are the same. In terms of our labeling or our organizational structure, we label the pins alphabetically with capital letters. If we then looking for the force in these, we have, for example, this would be member AB. The force in this would be labeled as FAB. All right, so AB refers to the member, FAB refers to the force. The first step in our analysis is going to be the same throughout this entire unit. We're going to do a free body diagram of the entire structure. That, of course, will include all the dimensions, other information, angles, etc., and any applied forces, weights, and reactions. We will remove the supports and replace them with reactions as we've been doing the last couple of units. In terms of the equations, we're going to be able to use sum of forces in the x, sum of forces in the y, and sum of moments about A. A can be any point in the plane, but we usually pick it to be convenient to eliminate unknowns. Keep in mind, you can also substitute moments about another point for one of the force equations. So moments about a point B or even a point C. We are limited to solving for 3 unknowns, however. We only have 3 independent equations, so that's our limitation in terms of this analysis. Generally, what we're going to be solving for is the reactions at whatever is supporting our truss. So we'll be limited to 3 unknowns, although we have some other ways we can increase the number of unknowns. We'll talk a little bit more further into the unit. So if we take a look, here's the free body diagram of that same truss. It includes the reactions here at A. There's a horizontal and vertical one because there's a pin. There is just a vertical one here because there's a roller. Right? And of course, these are the two applied loads. These are assumed to be frictionless pins, and the members are assumed to be weightless. Now, the next step. So it turns out it depends on how you want to analyze the structure. We have two methods available, known as the method of joints and the method of sections. Both of them are designed to determine what is taking place inside the actual members. So what's the internal force of the members? And to do that, we're going to divide our structure into sub-assemblies or sub-analysis. We can use the method of joints, and what we're going to do now is analyze each of the individual joints. So we essentially divide it there and look at the forces acting at a joint. They need to be in equilibrium. So we're going to use a calculation involving forces all acting at the joint. Or we can use the method of sections. In this case, we actually slice the truss or assembly up into a series of linked parts, and we look at that as its own structure, and we would analyze it using our equilibrium conditions. Let's start with the method of joints. It's the simpler of the two methods, and from what we learned from there, we can then build on that in the method of sections.